Okay, so in this video I'm going to have a look at the Maclaurin and Taylor series. I've written both of them out here. We're going to have a look at them. We're going to have a look at what they are, how you derive them, and when you would use them. And also we'll have a look at an example. So the Maclaurin and Taylor series are both basically the same things. Like a square, if you like, is a special type of rectangle. The Mclaren series is a special type of Taylor series. Okay, so when do we actually use them? Let's have a look. Let's say we have a function. Now, let's say we have our x and y axis, and let's say we have some kind of function like this, for example. Now, this is 0 here, and we have f of x up here. This is our f of x here. This is our function f of x. Now, if we have this particular function and we're really only interested in this function around 0, around this part of the graph here, we're not interested in what happens out here or down here. What we can do then is we can use the Maclaurin or the Taylor series. The Maclaurin series in this particular case, because we're only looking at x is equal to 0, to approximate this particular function around 0. That's what the Taylor series and Maclaurin series do. They take functions and approximate them around a particular x value. The Maclaurin series will take an x value of 0. The Taylor series will take any other x value. So if we're only interested in this part of the graph here, we can approximate this function by using the Maclaurin series. Now, this may be useful in cases where our function is not very nice to use. If we want to do things with the function and we find that it's difficult to do, then we can translate or approximate the function into a power series or a polynomial. If, for example, we're interested in, or we're looking at, let's say, a pendulum, and what we're going to do is look at the pendulum swinging like this, back and forward like this, and we're interested in the height the pendulum is above a certain distance, let's say this dotted line here. Now, the pendulum is going to swing from here to here, and this is your angle, let's say theta here. You can see that theta is never going to be too far from 0. So that would be one example where we might be looking at a function where we're just interested in an x value, in this case theta, that's not too far from 0. Let's have a look, and you know this particular example here would involve maybe some kind of a trigonometric function, and maybe we would prefer to be using a polynomial function or a power series function. So we would just look at the function around 0 and approximate our function, our trig function, by translating it or transforming it into a polynomial function. That's what our Maclaurin series will actually do. The other thing to remember is that your function must be infinitely differentiable. You can see here that we're using differentiation here, where n goes from 0 to infinity. So the function must be able to be differentiated an infinite number of times in both cases here. So if we take our function here, we can approximate this red function here, f of x, using a horizontal line. So if I was to draw a line through f of x here like this, we could say, well, y is equal to f of x here. That could be our approximation. But you can see here that while it's accurate at x is equal to 0, once we move slightly to the right or slightly to the left of 0, the function isn't quite accurate, because we're introducing an error here, and here you can see there's a gap between the actual function and the horizontal line. So what we could do then is maybe look at making sure that the first differential, or the slope at x is equal to 0, is the same in both cases. So if I was to draw a line like this and say, right, that's our approximation for f of x, you can see now the error is a lot less, but still it's not a great approximation. So what we can also do then is maybe say use a quadratic polynomial. So our quadratic might look something like this, so it's kind of hugging the curve a little bit better. We can even go further, we can go to a cubic. So our cubic curve might look something like this, which is going to hug it even better. And now you can see that the error is quite substantially reduced on either side of 0. And the further out we go, you know, to quartic and quintic and so on, we can see that we're going to get better and better approximations to our function around x is equal to 0. So let's have a look at deriving these formula that we started with up here. And remember, I will have a look at an example of how we're actually going to use these later on. So, but let's derive them first anyway. So I'm going to start with we'll start with the Maclaurin series. So we're going to start with the Mclaren. Yes, the Maclaurin series formula. And we're going to say that our function f of x is equal to some polynomial. So we're going to use our constants, which are going to be c0 plus, let's say, c1 is going to be our second constant, and that's multiplied by x. Our third constant is going to be c2, and that's going to be x squared. And then our next one is going to be c3, and that's going to be x cubed plus all the way out to c, let's say, n, and x to the power of n. So this is our polynomial that's going to replace our original function. Now let's look at x is equal to 0. You can see that at x is equal to 0 here, on the left hand side we'll just get f of 0, whatever that might be. And on the right hand side then, if we replace all the x's here with 0, we're just going to be left with c0. So let me just put that in a different color here. So I'm going to look at f of 0 is just going to be equal to c0. So we've worked out our first constant. c0 is just going to be f of 0. Now let's have a look at differentiating then. So we're going to differentiate this function. So we're going to look at, in other words, f prime of x. Now if we were to differentiate this function up here on the right hand side, well, if we differentiate c0, we're just going to get 0. We're differentiating a constant. If we differentiate this here, we're just going to be left with c1. If we differentiate this here, we're going to be left with 2c2 x, and so on, 3c3x squared plus all the way out to n times cn x to the power of n minus 1. So if we put 0 in for x, then we want f prime of 0 on the left hand side. On the right hand side, if we put 0 in for all the x's, we're just going to be left with c1. So now we have our second constant, our coefficient here, c1 is equal to f prime of 0. Okay, so let's go again then. Let's do the next differential. Let's do the second differential. So we're just going to differentiate this function here. Again, if you differentiate c1, you're going to get 0. If you differentiate this here, you're going to get 2c2. Out here, we're going to get 3 times 2c3x. So all I've done is taken the 2, brought it down here, and I've just, rather than writing 6, I've written 3 times 2, c3 times x. Okay, the next one out here would in fact have been 4c4x cubed, which I didn't put in, and so let me just do that one then. Out here you would end up with 4 times 3c4x squared, and so on, all the way out to n minus 1 times n cn x to the power of n minus 2. Okay, so let's now look at what would happen if we put 0 in for x on both sides. So on the left hand side, just going to get f double prime of 0. On the right hand side, all of these here will just give us 0. So we're just going to be left with this here. So we're going to be left with 2c2. So in other words, C2 then is just going to be equal to f double prime of 0 over 2. Okay, so let's go again then. So we're going to have a look at f triple prime x. So again, if we differentiate this, we're going to get 0. If we differentiate this, we're going to get 3 times 2 times C3. If we differentiate the next one, we're going to end up with 4 times 3 times 2 times C4x. And out here we're going to end up with n minus 2 times n minus 1 times n cn x to the power of n minus 3. Okay, you can probably see what's happening at this stage. So let's look at f of f triple prime of 0 here. So again, if we put in 0 for all the x's, all of these will disappear. So we're just going to end up here with 3 times 2 times 1, if you like, C3. So that will give me C3 then is equal to f triple prime of 0 all over 3 times 2, and I'll put in the 1 as well here if you like, 3 times 2 times 1. Okay, so that's 3 of them done. Now you can probably see what's happening here. If you look at these here, you can probably see the pattern, and it even works back up here as well. What you'll find is that f, our function differentiated n times, is going to be equal to n factorial times cn. So you can see these are this is 4 factorial, 3 factorial, and so on. So it's this would just mean then, this is just going to mean then that our cn is going to be equal to f n here of 0. So if we differentiate our function n times and stick in 0 for x, and then we've got to divide that by our n factorial. So this is where our first formula comes from. Just going to use this here. So our first formula, remember, was for the Maclaurin series was f of x is equal to the sum where n is equal to 0 up to infinity. Now we're going to use this here. So it's f differentiated n times, and we've got to stick in 0, remember? And underneath then here we've got n factorial. And we're going to have our x as well to the power of n. So if we look at this formula here, we can just work backwards to work out our polynomial. So for example, if n is equal to 0, we'll end up with a 0 up here. We'll have 0 factorial here, which is 1. We'll have x to the power of 0, which is 1. So really our first term will just be f of 0. We've got to add then, because remember we're adding all of these terms together. And if n is 1, we'll have 1 up here, so that's f prime 0, divided by 1 factorial, which is 1, and x to the power of 1, which is x, or second term is going to be f prime of 0, divided by 1, and then just x to the power of 1, which is x. Our third term will be f double prime of 0, divided by 2 factorial, or just 2 times 1 if you like, x squared. Our next term will be f triple prime of 0 divided by 3 factorial, 3 times 2 times 1, x cubed, and so on. So this will be our C1 here, this here will be our C2, this here will be C3, C4, and so on. Okay, but so what if we don't want to approximate our function around 0, x equal to 0? Let's say we want to approximate our function around some other x value. So let's say we go back to our original function here. Let's say we want to approximate our function around some value here. Let's call it a. And we're only interested in maybe this part of our graph here. What do we do? Well, in this particular case, we're going to end up with this function here, or this formula here, I should say, and the only difference between this formula and this formula here is that we have an x minus a out here to the power of n instead of just x to the power of n. The rest of our coefficients here are going to be the same. Our function differentiated n times of 0 divided by n factorial and so on. Okay, so let's look at deriving this. It's basically the same thing again. So I'll run through it maybe a little bit faster. But our function, original function again, f of x, is going to be given by c0 plus c1. This time, instead of x, it's going to be x minus a plus c2, x minus a squared plus c3, x minus a cubed, and so on, all the way out to cn, x minus a to the power of n. So in this case, if we look at f of a, we can see here that all our terms will disappear except for the first one, because we'll have a minus a, which is just 0 in each particular term except for the first one. So our f of a is just going to be c0, so we have our first coefficient, our first term, if you like. So let's differentiate our function. We've got f prime x. Our first term here will just disappear, so our second term will be c1. Third term will be twice c2 x minus a. Third term will be 3 times c3 x minus a squared, and so on all the way out to n times cn x minus a to the power of n minus 1. So if we do, let's see, f prime a, so in other words, substitute in a for x, all our terms will disappear. So our second constant here, our second coefficient here is c1, which is just f prime a. So let's just continue on, same as we did before. So we differentiate the second time, and our first term here will disappear. Our second term will be twice c2. Our third term will be 3 times 2 c3 x minus a, and again so on all the way out to n times n minus 1 cn x minus a to the power of n minus 2. So again here, let's have a look. We do a here instead of x, so substitute in a instead of x. All of these terms out here will disappear because we'll end up with zeros in here. So our f double prime of a is going to be equal to 2c2, which again just means that c2 is going to be equal to f double prime a over 2. So you can see we're doing exactly what we did above, so I'm not going to continue this on. It's the same procedure as we did before. So we'll end up with a similar formula. Our coefficients effectively will be f differentiated n times of a. We've got to divide by the n factorial. We're multiplying that by x minus a to the power of n. We've got to just add all of these up, where n is equal to 0. N goes from 0 to infinity. So this is our formula for the Taylor series, very similar to the Mclaren series formula. Now, just one thing you should take note of, and that is that not all functions can be approximated using the Mclaren series. For example, the log of x can't be approximated because you can't find the log of 0. It's undefinable. So let's have a look at a function that we can find an approximation for, and that's going to be the function e to the power of x. So we have our function f of x is equal to e to the power of x. Now this is not a difficult one to do because we know that if we differentiate e to the power of x, we get e to the power of x. So we can differentiate it loads and loads of times, and we're always just going to get e to the power of x each time. So again, our formula here is the sum where n is equal to 0 to infinity, and we're going to differentiate our function, let's say n times, we're doing the Maclaurin series, so it's going to be around 0 divided by n factorial, and we're going to multiply by x to the power of n each time. So let's start with n is equal to 0 for this particular function. So if we take n is equal to 0 here, we can see that this is going to be 0 here, so we're just looking at f of 0. So our f of 0 here is going to be e to the power of 0, which is 1. So we're going to end up with 1 up here. 0 factorial is just 1, so 1 over 1. And then we have x to the power of 0, which is 1. So our first term, all of this is just going to become 1. Let's look at n is equal to 1. So now we want the first differential of our function. So our first differential of our function is just going to be e to the power of x, e to the power of x, and e to the power, remember our x is 0, so it's going to be e to the power of 0, which is 1. And on the bottom here we have 1 factorial, which is 1, and then we'll have x to the power of 1 here, which is x. So it's just 1 times x to the power of 1, which is just x to the power of 1, which is just x. Okay, so our second term is just going to be x. So let's look at n is equal to 2 then. So n is equal to 2, so we want the second differential of our function. So again, it's just going to be e to the power of x. We want x to be 0, so e to the power of 0 is just 1, so we've got 1 on the top here. Now we've got 2 factorial here, so that's just going to be 2 factorial on the bottom, so we got 1 over 2 factorial, and then we have x to the power of 2 here, so x squared. So really what we end up with here is just x squared over 2 factorial. Let's look at n is equal to 3. So you got the third differential of our function. So again, that's just going to be e to the power of x. Put 0 in for x, so e to the power of 0 is 1. So we've got 1 on the top. We've got 3 factorial on the bottom here. So 3 factorial down here. And we've got x cubed up here, and that's it. And you can see the way it's going here, we're going to end up with x to the power of 4 over 4 factorial, and so on. So this is our approximation for e to the power of x. Our general term for this particular power series or polynomial is going to be x to the power of n over n factorial. So you can see that will work for any particular term. If we take our first term here, for example, n was 0, so x to the power of 0, x to the power of 0 over 0 factorial. So x to the power of 0 is 1, 0 factorial is 1, so it's 1 over 1, which is 1. So that'll give us our first term. If x is equal to 1, we'll get x to the power of 1 over 1 factorial, so that'll just give us x, that's our second term, and so on. Okay, so let's have a look at our approximation here. We have 1, 2, 3, 4, 5 terms here. What I've done is I've drawn the actual graph of e to the power of x, and then I've drawn graphs of our approximations using 1 term, 2 terms, 3, 4, 5, and 6 terms, just to see how close they look graphically. So let's have a look at those then. So this is my first approximation here. This is just x is, or y is equal to 1, I should say, so it's our horizontal line here. It's accurate at x is equal to 0, but once you go slightly to the right or slightly to the left of 0, you can see we're introducing quite big errors here. So we take 2 terms then. This is our approximation using 2 terms, 1 plus x. So the slope of our approximation here in blue is going to be the same as the slope of the tangent at x is equal to 0 for our function. So you can see it's a little bit more accurate than our horizontal line. So let's just look at our next one. This is 1 plus x squared over 2. This is our quadratic, and you see it does hug the line quite well around here. Once we get out here, we start to see the errors a little bit further out, so it's a little bit more accurate again. If we use another term, 1 plus x squared over 2 plus x cubed over 6, you can see it's hugging the actual curve quite well now. So it depends on how far out you want to go, really. I've done another 2. This is the quartic, so this is quite accurate around x is equal to 0 around here. And then if we go one more, this is the x to the power of 5 term. So you can see it is quite accurate here around x is equal to 0. Now, one thing we've got to look at here with this series is the radius of convergence. So we've got to look at or being equal to the a n plus 1 over a n. Got to look at the modulus of this, and just to make sure that this series actually converges. So our general term is this one here. So what we're going to do is look at x to the power of n plus 1 divided by n plus 1 factorial, and then we've got to divide that by the previous general term, if you like. So that's just x to the power of n over n factorial. This is our or, and we've got to look at the modulus of this here, if you like. So let's just do this, and just let's make sure that this is less than 1. We want this here to be less than 1 so that the series converges for all values of x. So let's work through this then, just to make sure that it is. So this is going to be equal to x to the power of n plus 1 over n plus 1 factorial times n factorial over x to the power of n. Now if we simplify this, if we have a look at this one and this one here, you can see that x to the power of n plus 1 divided by x to the power of n will just give us x, and n factorial divided by n plus 1 factorial will leave us with n plus 1. So we want to see what the value of this term here will be as n goes to infinity. So as n goes to infinity here, we can see that the denominator here will go to infinity, which means this whole fraction here will just give us 0. So in other words, we're finding the limit of this, if you like, as n goes to infinity of x over n plus 1. We can see that 0 is less than 1, so the series does converge for all values of x. Okay, so that's really it for the Taylor and Maclaurin series.